Welcome, everybody. Good morning. Our first presenter of the day has been a member of the Nutmeg Division all the way back 2013, Secretary of the Farmington Valley Railway Society, and a board member of the Canton Historical Museum. Retired training supervisor for Honeywell Fire Systems. He models in HO, and his home layout is undergoing some preliminary right-of-way leasing talks. Welcome, Mr. Jim Kline.
Well, thank you, Speed. Hello, everyone. It's great to be here. And I just want to let you know that I'm hearing two things going on at the same time, and I just muted the other Facebook. But anyway, hello and welcome. My name's Jim Kline, and in this clinic, we will discuss what it takes from a planning perspective to put our ideas to light something, to move something, or sense something on our layouts into a format that can be used to write the code for an Arduino. Then we'll look at how the code for a traffic light would be written in Arduino code. Whether you are planning on writing programs, sketches in Arduino speak, or merely want to learn how to describe what you want an Arduino to do, this clinic is for you. No prior programming experience is required, so put your calculators away. We're going to be using a traffic light as an example to illustrate how to organize workflow such that our programming effort will be as efficient as possible. The traffic light example will provide us with basic instructions that can be used on a layout, such as controlling crossing signals, operating turnouts, acting on inputs from an occupancy detector, for instance, and even activating signal mass, etc. The possibilities are endless. Pictured is the Arduino Uno. And for your first time, I strongly recommend that you begin with the Uno. Later, you can explore the other versions, but get your feet wet with the Uno first. Most of the tutorials and YouTube videos that are available feature the Uno. You can get bogged down in trying to figure out how to modify the Uno code to make the example work on a non-Uno Arduino. The Uno was designed so that it could be easily reused for successive experimental projects. The connection strips on each side of the Arduino PC board are female headers that accept male jumpers to connect to external circuitry such as LEDs, lights, switches, potentiometers, etc. Additionally, there are breakout boards called shields that are designed to mate with the female headers that can control motors, servos, and the like. There are many examples of code that are included automatically in the free software download for programming an Arduino. They provide you a proven sketch for experimenting with an Arduino. One of the sketches is called Blink, which is a very basic sketch that will blink an onboard LED on the Arduino. A very handy sketch that will prove that your Arduino is operating and is able to accept the download. No wiring needed other than a USB cable that connects between your computer and the Arduino. I use the blank sketch when I get a new board, much the same way you would check a new calculator by adding 2 plus 2 and checking the result for 4. Often a new programmer will just jump in and start pounding out code. While enthusiasm is commendable, it helps to know the basics first. It's not impossible to start programming immediately, but it can become very frustrating, time-consuming, and ultimately the finished product will look like a plate of spaghetti. Spaghetti code is a pejorative term used by those that code for a living. Consider the individual spaghettis. They twist and turn and travel willy-nilly all over the plate. There is nothing regimented or orderly about them. Code is a very sequence-driven animal. Code in general is a top-down, organized sequence of instructions to achieve a particular outcome. The more complex the job or functions the code performs, the more prone it is to becoming spaghetti code. And spaghetti tends to become unstable very easily. Can you say blue screen of death, Microsoft? Storyboarding has been used effectively for a very long time for plays, movies, cartoons, processes, and programs. Essentially, what one does using storyboarding is describe in logical sequence what is supposed to happen. We will be doing just that today, but before developing code, let's look at a fundamental aspect of Arduinos and all other computing devices. Microcontrollers, computers, etc. are very myopic. Some of you might recognize this cartoon character. This individual was very nearsighted and could barely see beyond the end of his nose. In much the same way, computers are identical. They only concentrate on what is before them and will continue with a single-minded purpose until instructed to do something different. Trivia question. What actor provided the voice for Mr. Magoo, and what famous television sitcom did that actor star in? To illustrate the point of computer myopia, consider a DCC-equipped locomotive. Using your throttle, you start up your train and get it up to speed on the main line. You then disconnect the throttle, walk down the layout, and reconnect the throttle to a new interconnect panel. What happened to your train while the throttle was disconnected? Nothing. The locomotive kept moving using the last setting it received from you via the throttle. It would have continued to run at that setting until it met an obstacle, derailed, or some other bad event intervened. The point is the decoder, in this case microcontroller inside the decoder, installed in the locomotive will faithfully continue to execute its last instruction until told to do something else. Understanding that fact will help you to write code in logical fashion, or if you're not going to write the actual program, be able to present to your programmer a specification that clearly defines what you want to happen. To do that, a human readable format was developed known as pseudocode. Pseudocode is similar to storyboarding. This allows anyone, programmer and non-programmer alike, to write a logically sequenced specification that can be used as a guideline for what the final program should do. There are three basic tenets to pseudocode as shown here. Let's say that you are going to have someone write the final code for you. That would be your target audience. However, if you plan to write the code yourself, then obviously you are the target audience. Note, this first step is where things can derail very quickly. Don't skimp on this or take shortcuts just because you already know what you want to have happen. Next, by maintaining a logical sequence and being consistent in how you name things, that satisfies the second bullet. Finally, the most important step is to make certain that you have defined the entire process and left nothing out. We all know that famous line uttered by a boss or a salesman partway into a project that upsets everything and goes something like this. Wouldn't it be neat if? Or the other classic that my wife seems to prefer when talking about the honey-do list, all you have to do is. Before I wised up, I would say to her, well, if it's that easy, why don't you do it? I don't say that anymore. Consider a traffic signal protecting and regulating traffic flow at the intersection of two streets. Not much to it. We've all seen one and know exactly how it operates. But hey, shouldn't we be talking about something a little bit more complex? We could, but as you'll see, the traffic light has a higher level of complexity than it appears. The first requirement to writing code is to know what the sequence of operation is supposed to be. So to help keep things organized, I'll use a spreadsheet laying out the sequence of the green, yellow, and red light activations of the traffic signal. Part of the design process includes what pins on the Arduino will be assigned to the lights. We will not assign them at this point, but we have made a decision that the lamps on the opposite side of the traffic light will be in parallel with those on the front. And that way the same light pattern will be on the South Street face as on the North Street face. Same goes for the East and West Street faces. Knowing how many pins you will need is very important when choosing a type of Arduino that you use. The Arduino family has several types, and they don't all have the same pinouts. If the design called for independent control of each of the four faces, the spreadsheet could be expanded to include the additional faces. The design might also include turn-only arrows as well for each of the four streets. Wow, we've barely even started, and the potential complexity level just rose significantly. As you study the spreadsheet, notice at step 1 that it begins with the north and south streets having a green light. Let me get my laser pointer here. Traffic is allowed to flow on the north and south streets. What about the east and west streets? Well, it's obvious choice. It's going to have to be a red light for the east and west streets. The same applies when the north-south street turns yellow. East-west streets got to have a red light as well. But when the north-south street turns red, then the east-west street can turn green. And then the east-west street will be green for a while. It turns to yellow, and the north-south street obviously would still have a red signal. So that's one part of the sequence of operations for the traffic light. The other is putting in the amounts of time that we want to have the delay between one signal turning on, then turning off and transferring over to another signal. In this case, we need to assign a delay time. I'm going to compress a little bit. We'll have 10 seconds for the green to yellow transition, and then 3 seconds for yellow to red, and then repeating. So now we have a complete sequence of the traffic light. But that's not how today's traffic signals operate. Today's traffic signals operate on what is known as a delay green, such that when a previously active traffic flow is halted by a red traffic light, the cross traffic light will not immediately turn green, but hold the red light on for a short period of time. That way, you prevent crashes, supposedly, for people trying to beat the light. As before, we need to develop the sequence of operation to add this feature to the program. So as you see, the sequence of operation now would be complete, where we have a delay green format. And now it's time for us to assign these pins associated with the various LEDs. This is an important step for a number of reasons, but when making a schematic, it is helpful to follow a recognizable format. The top-down order of the red, yellow, and green LEDs are in the same order as seen on an actual traffic light. It makes it easier to read the schematic. The Arduino will be supplying power to the LED pairs, and the drawing remains uncluttered by wiring the pins one after the other and not crossing any lines. One other thing to note is these labels here for the wiring to the individual pairs of LEDs. And notice how this drawing is nice and clean. The wires to the various LEDs go straight across, no crossovers. So we used a schematic of the Arduino to identify the 6 Arduino pins that will control the on-off conditions for each of the lights. We also labeled each of the pins to help us remember what each pin is controlling. The letters R, Y, and G are used to indicate the color of the light or the LED, plus a prefix of NS or EW, which yields an easily identifiable label. For example, NSR is the pin that activates the red light on the north and south faces. A little later, you will see how convenient good labels are in good code writing in a code writing effort. Note, the Arduino can only power a limited amount of devices. Excuse me. For this project, there were only 2 sets of LEDs on at any one time, and that will not tax the Arduino's ability to power them. If, however, we were planning on activating a high power device, for example, a 12-volt automotive bulb that draws several amps, the Arduino wouldn't be able to handle that amount of power directly. However, you could install an interfacing, an interfacing circuit, such as a small transfer relay, that will then use the power handling ability of its mechanical switch to activate the lamp directly from a separate power supply from the Arduino. So we just listed in great detail here the sequence of operations needed for a traffic light. And in written format, here is that Arduino code juxtapositioned against the spreadsheet. And as you can see, if you follow top down for the pseudocode, you're going to start with all the LEDs off. We want to know where we're starting from, so we want to have a preset condition. And then we start with, we're going to turn the north-south green LED on and the east-west red on. We're then going to delay 10 seconds, north-south green off. We got to turn remember, it's myopic. We have to tell it that we no longer want the green on. We want something else on, in this case, the yellow, and so on and so forth as you develop. That's the entire code for a delayed green traffic light. Now, you're taking a look at it and you're saying, well, I've got instructions one after the other, so there might be a little bit of a lag. Well, understand the fact that with an Arduino, as all microcontrollers, et cetera, today, they are operating so quickly, they're able to execute several thousand instructions per second. You're not even going to see any kind of a flicker or anything like that. So at this point, you could take that pseudocode and hand it off to a programmer along with the schematic, and you could say, okay, write me the code, download it into the Arduino, and bring it back to me, and I'll set it up on the layout or wherever I plan to use this particular sketch. So we could do that, or we could just go ahead and decide that maybe we ought to take a look and see how the code is developed from this point. So the thing here is that we're going to modify a little bit, and I say, let's keep on going. The integrated development environment. Before writing code, we need a place to put it. The IDE is where all the information lives regarding the sketch. Its job is to organize the attributes and instructions that make up the component parts of the sketch. It uses a text editor program similar to Windows Notepad, and has some helpful features that will be discussed as we use them today. For starters, when a new sketch is opened, a practically empty work area appears, as you see here. There are two basic sections of the IDE, a setup area where certain properties that need defined and preset are placed, and the loop area where the sketch instructions are placed. And the loop area is where the code continuously runs. We have been working on the pseudocode of our sketch for about the past 15 minutes or so, and we will place that code in the loop area in a slightly different format. Note that the function of each section is displayed using the comments feature of the IDE. Anything that starts off with 2 forward slashes is deemed a comment by the IDE. And even though we will be writing code in here, when the IDE goes to create the actual code that's going to get downloaded to the Arduino, it will ignore those comments. Before we start converting the pseudocode into a sketch, there is a certain amount of preliminary setup work that needs to be done. We discussed the 6 pins that the Arduino will be using to illuminate the 6 different LEDs on the traffic light. I know that there are actually 12 LEDs, but the 6 pins are activating pairs of LEDs. Earlier, we indicated that it was important to provide an easily recognizable label that can be used to identify the 6 pin numbers on the Arduino, rather than trying to remember actual pin numbers. In addition, the 6 pins need to be designated as output pins. If it wasn't made clear before, the Arduino's pins can perform multiple functions, but not simultaneously. For now, we'll just discuss 2 of those functions, and they are input or output. The only way the Arduino knows the function of a given pin, input or output, is when it is properly identified within the sketch. The side-by-side comparison of pin connections to the UNO and the IDE code that assigns the number of the Arduino pin to a text descriptor. We're going to use that later. So right here, for instance, line number 2, we have defined NSR as being equivalent to 12. That's pin 12. North-south red is 12. North-south yellow is 11. North-south green is 10, so on and so forth. So we've just told the sketch right here that we're making these assignments to those labels or vice versa. The next thing we need to do is to assign a mode for each pin. All the pins are outputs, so we enter that information in one line at a time. And as you can see here, down here in the setup area, we've assigned pin mode to north-south red, which is the equivalent of pin 12. We're saying that that's going to be an output. And we did the same all the way down through the remaining 5. And take notice here, all these pin mode descriptors here were red or are red, except for this guy right here, this last one for east, west, green. It's blacked out. The reason why is I typed it in incorrectly by not capitalizing the letter M. This is one of the features that I was talking about of the IDE that helps keep you out of trouble. Not all trouble, but a lot of it. When the Arduino first powers up, there is a remote possibility that the status of the output pins may be unknown. So prior to running the main code, a preset instruction is performed in the setup area so that we preset the exact state of each pin at startup. So we've expanded a little bit here. We're now broadening what's happening in the code, and we're saying, look, I want to write digitally. I want to set that pin to a low. Remember, we have the anodes of the LEDs connected to the pin of the Arduino. When that pin goes high, there's 5 volts on it, and the LEDs will light. If that pin is low or 0 volts, it won't light. So for each one of the 6 pins, we have said in the beginning part of the code here, I want all outputs to be off. Sort of like an insurance policy. So now we have the completed loop function next to the pseudocode. I've taken and written all the different things that we have been talking about as far as the traffic light code, and we've put it in a format that the Arduino can recognize. So we'll start off here at the north-south green. We're going to write to that pin. We're going to make it high. Remember, we're starting the program now. This is where the traffic light is going to function. We also have to turn the east-west right on. The east-west red on. See, that's 3 times without drinking a beer. Then we're going to delay for 10,000 milliseconds. A millisecond is a thousandth of a second, so 10,000 of them yields 10 seconds. After that delay period is over, we're then going to turn the north-south green to low. We're going to turn it off, and we're going to turn on the north-south yellow. We don't have to do anything about the east-west red because we've already told it to turn on. So as you go down through, it's the same format all the way through. Once the program reaches this point here, down at line 46, it just flips back up and it starts all over again and just keeps on executing until you turn the power off. So now, this is the entire sketch needed to operate the traffic light. You've got the setup area and you have the main code. At this point, you could actually compile this code, and by compile, I mean the IDE will take this code that you laid out here on the IDE, and it will place it into a format that the Arduino can understand, and then you download it to the Arduino, and that program now is resident in the Arduino. You hook up the LEDs to the 6 pins, and you should have a traffic light scenario running for you. So now that we have a basic traffic signal, what would it take to add a pedestrian button that will stop the flow of traffic in both directions and light a light to let the pedestrian know that the system has been paused for a preset amount of time and it's safe to walk across the street? You got to be careful about this one because care must be taken as to where and how we write the code so that we do not inadvertently change the traffic pattern when the button is pushed. The traffic flow sequence can't abruptly change and call the street that has traffic flow change from green to instantaneous red. The code design must allow the normal sequence to proceed until it arrives at the delayed green section, and then it can hold traffic for an additional amount of time for the pedestrian to safely cross. So we need to add some things. We're going to have to add a momentary push button switch for the pedestrian to activate in order to pause the traffic flow sequence, and a light to indicate that the traffic light sequence has been paused. As before, the pins to be used on the Arduino as before, pick the pins to be used on the Arduino and assign a label to each. The project is growing and 8 pins of the Arduino are now used. To activate the new LED, the digital write command is used as before. However, the pedestrian button is something else. The code needs to know when it has changed state. The button is a normally open button with a resistor connected to 5 volts. The resistor is there. It's called a pull-up resistor, and it's there such that whenever the button is not pushed, we always have a high value or 5 volts on that pin. I've expanded or carved out a small area of the schematic to make it easier to see. As before, the pins and their labels will need to be identified in the IDE. Obviously, there are parts of code missing here, but hopefully you know where to place this new code in the sketch. I didn't explain earlier about the curly braces. As seen in the setup area, the code contained between these serial braces, the code contained between these curly braces defines and encapsulates that area. Now, it's not uncommon to find curly braces inside of curly braces, and we'll talk about that in just a couple of minutes. In order to know when the button is pushed, we need to read pin 6 and determine its state, whether or not it's high or low. To do that, we will use a function that resembles another function we used earlier, digital read. Looks almost identical to digital write, doesn't it? Another important point is that you may have noticed the use of semicolons after each line of code. That's important because that tells the compiler when that line of code is finished before proceeding to the next code and next line of code. We got to talk about a couple more concepts. As you see here, a variable is nothing more than a container. This, for instance, in your decoders, we have CVs. Those are variables. V stands for variable in CV, and you place a numeric value into that in order to achieve whatever that particular CV controls. Same here with the Arduino. Now, variables can be of different types. We're going to be concentrating on integers, whole numbers, and we're going to be using integer variables. Another important point when you're looking at writing code, and that is a single equal sign assigns a value. The variable on the left side of the equal sign will be assigned the integer value 15. The variable a will then contain the value 15 until a different value is assigned to it or power is removed. A double equal sign is used to evaluate or test. We can read the state of the pin attached to the push button, but where do we put the code? We could place the code to read the button after or before each delay. However, it is highly unlikely that the pedestrian will push the button at that exact instant. There should be a way that the program continuously checks to see if the button has been pushed. Actually, there is more than one way, but we will use a basic repeating loop structure known as a for loop to perform that task. Using a for loop allows the sketch to constantly check the status of the button approximately every 50 milliseconds. Different delays can be used other than 50. The for loop runs in place, so to speak. It works by making successive passes, and another way to think of it is as a step counter that increments by 1 on each pass. The for loop starts by setting the variable little I, or small lowercase I, to 0. Next, the sketch performs the instructions contained within the curly braces. When the delay time reaches 50 milliseconds, the for loop repeats the process by adding a 1 to the variable I, and then checks to see if the variable I is greater than 200. As long as the variable I value is less than 200, the instruction contained within the curly braces will be executed. This set of instructions, execute 200 times, has effectively generated a delay of approximately 10 seconds and was able to do work while the delay was delaying. This code can be substituted for the 10-second delay in the sketch. With a simple modification, the other 2 delays for 2 seconds and 3 seconds can also be done. Question: what needs to be changed in order to generate a 3-second delay and a 2-second delay? We check the button at each pass, but even if the button was pushed, we don't have a way to use that information. We need a container, a variable, to hold the information that the button has been pushed. The variable name will be an integer type called cross. I picked that. I designated that variable's name to be cross. When the sketch reads a low on the PED button, P-E-D-B-U-T, the sketch will assign a value of 1 to the variable cross. The sketch can continue to read button activations. However, once the value has been loaded into the variable cross will always have the value of 1. Subsequent button activations will have no effect. There is a new statement being used called if. And by now you should be getting the hang of how to read these statements. The if statement operates by evaluating what is contained within the parenthesis. If it evaluates as true, then the statement or statements within the red curly braces are executed. If, on the other hand, it evaluates false, then the red curly braces are jumped over, and the next executed command will be the 50-second time delay. In order to reset for the next cycle, the sketch will need to clear the variable cross by placing a numeric value that is a non-1. This should be done in the area of the code that you will be modifying to implement a time delay for pedestrians to cross when both the north and south, east, west faces are red, which is during the delayed green cycle. In this case, I would suggest writing the code to place a 0 in cross once the code is active in the delayed green portion. So here's a code for halting the traffic light sequence for an additional period of time to allow a pedestrian to cross the street. Using the if control structure, the variable cross is evaluated, and if cross contains a non-zero value, which means that a button has been pushed, the code contained within the curly braces is executed. The actions taken by the sketch from that point are: turn the PED LED on, delay for 4 seconds, turn the PED LED off, and clear out the variable cross for the next button push. This new code will be placed in the delayed green section of the code. Keep in mind that there are 2 places in the sketch where delayed green is active. So here is a code with a 10-second delay replaced with a new code for loop. With a new code for loop that performs a delay function and also scans the PED button or PED pedestrian button for activations. Additionally, the code for the extra delay for the pedestrian to safely cross the street is included. Take notice that at the start of the main loop function, the new variables I and cross are declared as int or integer variables. By doing this, you don't need to place integer in front of each of them each time. You need to, whenever you're in a function, you need to identify the types of variables that you'll be using. If you don't declare them, then the compiler will return an error message to you that says, I don't recognize that. So you need to do some of this work up front. You can also do it up in the setup area, but that becomes a global variable, and that's a whole other discussion. So anyway, I'll leave it to you to complete the delay substitutions for the rest of the sketch. I didn't want to clutter up this code that you see here, I only put one instance of the delay for the button push, and then I put one instance of the actual area where you're going to execute and light the pedestrian light, and have the 4-second delay for the pedestrian to cross. Obviously, we have 3-second delays and another 10-second delay, etc., where this needs to be installed or substituted for those. So at this point, you should be getting the feeling that there is a theme here which says everything is a number. No matter the device or the content, everything is a number. The colors and images on your monitor right now, your smartphone messages and icons, everything reduces to and then is built up from a number. And because of that, we use these operator symbols or what have you, and we use them quite extensively in code. And it is important to be comfortable with their use. No pressure here. We're just going to do a quick and easy test. So making things easy to remember, we have a 1, 2, 3 ABC relationship. So let's see how your logic works here. So we're going to evaluate these true or false. Is A less than B? Is B less than C? Is C greater than A? If you answer true to all three, you are correct. Is B greater than A? Is A equal to B? B is greater than A, that's true. A is not equal to B, that's false. And if you were required to perform a little math here, with A equal to 1 and B equal to, what is the value of D? That would be 3. And now, what is the value of D? If A and B are equal to 1 and 2 respectively, and C is equal to 3, then the value of D has to be 0. So how did you do during that? The previous examples, assessing a variable and how it compares to other variables, is the bread and butter of coding. It is not my intent to minimize the complexity of coding, but to illustrate that when broken down into basic component parts, creating code for an Arduino is not the Herculean task many people believe it to be. The saying, if you can describe it, you can code it, applies here, with certain limitations, of course. If you were able to follow along today, I would strongly suggest that you invest a few dollars in an Arduino and see what magic you can create. As you can see, I screenshot this a few days ago. I was putting this presentation together, and at the time, a genuine Arduino was $23 plus $900 to ship it, but that's a whole other story. You only need your computer, a breadboard for parts such as LEDs, switches, and the like, to connect the Arduino's to the Arduino's female headers, and a USB cable to connect between your computer and the Arduino itself. Before closing, I would like to make an appeal that you give serious thought to presenting a clinic of your own, excuse me, at the division, region, or national level. If you are not a member of the NMRA, you can still give a clinic. And I want to thank you for your attention today. I hope you found this clinic informative. The links that you see here on the wrap-up screen, the Arduino, that's where you go to get information and to download the software for the Arduino. FVRS.club, that is the Farmington Valley Railway Society.club. We've got a 40 by 40 diorama there. Some of you have seen it already. And we have a freelance version behind the front diorama, which is for the museum itself. And you may find some interesting tutorials as well as product for Arduinos on adafruit.com. It's another good resource, I should say. So I'm going to wrap up today with a short video of the working traffic light using LEDs, but not discrete LEDs that we just wrote a sketch for. These are very special LEDs known as NeoPixels, and they are wired in series and only one pin is needed from the Arduino to operate them. The program flow is the same as the sketch that we just wrote, but the activation of the LEDs takes a different form than the pin mode command that we've been using. If you would like to learn more about NeoPixels and how they work, join me tonight at 8 p.m. for the NeoPixel Clinic. FYI, NeoPixels can be installed in Signal Mast and interfaced with JMRI. Again, thank you.
Jim, can you see the video?
All right, let me get rid of my one screen here. Where did you go?
If you can see the video, you need to talk to it.
Pardon me?
You need to talk to the video. The sound is not going through to the cloud.
You mean that whole thing? Nothing happened?
Your voice was not there.
Oh my goodness.
You can click rewind and do it again.
Oh, you mean for the video? My presentation was okay?
Yes, you played a video, but nobody could hear anything. We're still live, so don't worry about it. They can hear us talk.
Oh, okay.
So just play the video again, and then just tell us in your own voice what's happening.
Oh, okay. Okay, got it. Okay. All righty. Okay, what you're seeing here is a traffic light demonstration that uses NeoPixels as opposed to discrete LEDs.
Jim, you need
and the controller is not an Arduino. It
Jim?
is a small Adafruit Arduino family type of controller. It's got a limited pin out, but it fits into a 1-inch square package. And
Jim,
there's a push button, as you can see. There's also a switch that I can demonstrate, that I use to demonstrate the difference between delayed green versus a normal type of traffic signal sequence. And there's only 3 wires that drive that traffic signal mast, plus or minus 5 volts, plus the data signal that comes in. That little thing that I just pushed there, the blue light, that's a little 5-volt power pack. So that's how I set up a traffic signal to be operated or to demonstrate the code, but it uses NeoPixels. And by the way, those NeoPixels can be put in signal masts, etc., using JMRI as the code source. Okay. We still good?
We're good. Let's go to the questions.
All right. Now I can't hear.
Can you hear us?
Yeah, and I'm getting 2. There's a delay.
You have to stop Facebook or YouTube. For those people who want to give a clinic, that's requirement number 1. You cannot watch yourself. Only tomorrow. First question, who voiced Mr. Magoo?
Oh, for me?
Yeah, so
Oh,
the people would know
okay.
they're
I thought
right.
people had that was Jim Backus.
Cool. You got to feel right in the chat.
Yeah.
I noticed some colors in the IDE. Why are those
Hmm.
things different colors?
Well, the different colors indicate to you that you are uh, inputting the correct format that the IDE is looking for. For instance, when I did pin mode and I had the M for pin mode not capitalized, it had straight black. And when I put the or typed in the M correctly with a cap, then it turned red, indicating that it was a correct format understood by the IDE.
So when you created those pseudocode things to give to a developer, do you tell him if turnout number 2 is thrown or the route is diverging and the block is not occupied? Do you put it in that kind of words?
Well, you can. The trick is to be able to make it where whenever you're giving code to a programmer like that, you want to be able to make sure that that person also understands what it is that you're referring to. So you do have to have some upfront understanding as to the commonality of what it is that you're trying to express.
So I've seen some diagrams that has like circles and arrows, and I think they call them state diagrams. Could that be a
Yes.
tool to help
Yes.
pseudocode or?
Yes. I toyed with the idea of using a flow chart, using those types of decision trees and things like that. However, it's a lot easier to describe something in a format such as this, a 45, 50-minute format, as opposed to going through all the different explanations as to what a particular symbol would mean. For instance, a baseball diamond or what have you as a decision.
Mhm.
You know, yes, no, true, false, etc.
And then the last question, someone commented, this looks a lot like C code.
Yeah, it does, doesn't it? So if you go on up and Google Arduino code or what have you, you'll see that it's a basic C++ code.
Roger. Well, that's the end of the
Now,
questions. But so if you want to tell something more, we have 5 more minutes.
well, maybe my timings were off a little bit because I thought I was at the 47-minute mark when I practiced. But no, I really don't have anything more other than to say if anyone is interested and you're in the Canton, Collinsville area of Connecticut, we would be more than happy to entertain you for the day or for a couple hours, whatever. Bring your throttle over and you can run our layout. We've got, as I said, a 40 by 40 foot room, and there's a lot of rolling stock on it and a lot to do. And we're working on doing it operations. We're in the process of putting that together, which is I'm having fun doing.
Cool. Thank you very, very much. We're looking forward to the next one later today. So don't go too far away.